So today we are featuring Phinix and some of the developments they are investigating and taking a look at regarding aluminum die casting and some increase in strength while lightweighting at the same time. So we're looking forward to hearing that presentation. A few housekeeping items to take a look at real quickly. First, please put your phone or microphone on mute so we can hear the presentation and don't hear any background noise that may or may not be taking place in your office, in your home, wherever you happen to be. If you have questions, we'll have a Q&A session at the end of the presentation. If you have questions, please use the chat function that is part of the GoToMeeting taskbar well, it's on my right-hand side of the screen. And please send your questions to the organizer. That is me, and I will then facilitate the Q&A afterwards. So please send them that way, and we'll take care of it when the time comes for Q&A. And then finally, again, each Liftoff webinar will be recorded and posted on the Lift website for future viewing. Just a little bit about Lift. We are one of 14 Manufacturing USA institutes. We are based here in Detroit, and our mission is to accelerate the development and application of innovative lightweight metal production and manufacturing technologies benefit both the U.S. commercial and defense markets. So we have essentially three pillars: technology development in terms of lightweighting. Right now, our focus has been on transportation sector. If it moves people or goods, it can benefit from lightweighting, whether it's on the sea, on the roads, in the air, on the rails. There are some benefits that can take place through lightweighting there. The next mission that we have really is the technology transition. It is one thing to investigate that technology, is one thing to come up with some lightweighting solutions, but it is another thing entirely to help transition that technology into the marketplace. And that is really the crux of what the Manufacturing USA are about, not just the technology investigation, but also transitioning it into the marketplace. And finally, the third leg of the stool that we have is our education workforce development piece. That is really aimed at making sure the pipeline of workers is robust for manufacturing and engineering going forward. As I'm sure many of you have heard, the skills gap it exists in manufacturing. There are going to be millions of jobs open up over the next several years, and less than half of them will be filled because there are not enough people going into manufacturing and engineering as a career choice. So our goal is to help open up the eyes of folks we call it from K through gray. We have initiatives for elementary schoolers, middle schoolers, high schoolers, college students, and incumbent workforce members and veterans to really open up their eyes to manufacturing as a possible career choice. You can learn more about us at lift.technology. You can follow us on Twitter at newsfromlift, or you can give us a call. The phone number is on your screen. We're happy to answer any questions or let folks know anything else about us. I'll have something else that I want to talk about at the end of the presentation that you folks in the local Detroit area, or if you're making a visit to Detroit next week or in the next couple of weeks, you might be interested in. We want to thank the Michigan Manufacturing Technology Center. They have joined with us in this effort to lift off webinar series to highlight some of the smaller and medium-sized companies that are out there to really take a look at some of the innovations that they're working on, because we know that is where innovation takes place a lot of times, not necessarily at the big, large companies, but at these smaller companies where folks are really trying to get these innovations off the ground. So with that, I'd like to invite Edie to speak about the center over here in Plymouth.
Thank you, Joe. We at the Michigan Manufacturing Technology Center are the Michigan location of a national network funded out of the National Institute for Standards and Technology. And this national network is called the Manufacturing Extension Partnership. So I'm sure many of you who are listening today are aware of the Manufacturing Extension Partnership location in your own state. Because we are located so close to Lift, and because of our strong belief in the relevance of lift technology development for small to mid-sized manufacturers, we have been funded by the Manufacturing Extension Partnership to enhance our day-to-day working with the lift organization and to try to make it immediately relevant, particularly to small and mid-sized companies. So to that end, we have hired our design engineer, Greg Peterson, most recently of Lotus Engineering, who is really a master design for lightweighting specialist, and also very well versed in manufacturability issues with regard to lightweight materials and appropriate design and joining techniques. So if Greg is today presenting at the Aluminum Extruders Council on opportunities for extrusions that are expanding in automotive, so he can't be with us today, but any of you who are fall into the category of a small to mid-size manufacturing establishment with less than 500 employees, even nationwide, we'd be very happy to connect you with the lift resources and see what we can do to make lift technology applicable to your business. And to that end, you can contact Greg by giving us a call at the center. The number appears on the slide here today. And the Manufacturing Extension Partnership offers many other services as well, as are highlighted on the slide. Thank you, Joe.
Excellent. Thank you very much. Appreciate that. Appreciate that. And yes, we are keeping, Greg is keeping himself busy, both for Lift and the center. So I know he would have wanted to join us here today, but he is, as you said, out presenting. So with that, I'm going to turn things over to Dr. Adam Gessing at Phinix to get the ball rolling on the innovations that they are working on over at Phinix. So, Dr. Gessing, it is all yours.
Artificial agent strengthened aluminum superalloys. This new light metal composite is net-shaped form by high-pressure die casting with the potential to reduce mass by 40% and to reduce cost by 20%. A little bit of a background: the aluminum silicon alloys are the bread and butter of the aluminum foundry industry and are being cast at an annual rate of over 2 million tons per year in North America for use mainly in transportation. However, the coarse microstructure of these alloys limits their specific mechanical properties and their potential for vehicle lightweighting. A new development of a cast aluminum alloy produced in situ form nanocomposite of up to 25 volume% of submicron aqueous silicon particles in an aluminum matrix that can be left ductile or can be reinforced by nanoscale spinodal precipitates. The ultrafine microstructures of these new materials give them significantly improved strength, hardness, and wear resistance, while retaining adequate toughness and ductility for application in the transportation applications. These materials are produced by conventional casting technique, including continuous strip casting and high-pressure die casting. Some background: the hypereutectic aluminum silicon and alloys with other additives are excellent choices for high-performance cast components. They are already used for pistons, cylinder liners, and for monolithic linerless engine blocks. The high silicon minimizes the thermal expansion coefficient, and improves the alloy's thermal conductivity by almost 3 times in comparison with cast iron. as cast tribological property are mainly controlled by primary and secondary silicon morphology, but the hypereutectic cast component on the market now contain primary particles of up to 200 microns, and agglomerations of those particles lead to critical flaws that limit their application for strength critical applications. The industry demands significant reduction of primary and secondary silicon size for improvement of the component's mechanical properties. Optimum process conditions for melt treatment, solidification, and heat treatment are critical in obtaining the required mechanical properties. An example of the use of such a hypereutectic alloy, this is A390 alloy used in the engine block of a Yamaha Majesty motorcycle. It is formed by high pressure die casting, in which the metal is poured into dosing hole of a shot sleeve and then injected into the die cavity by the injection plunger. The microstructure that results is shown here. It is already heat treated, and it is dominated by large primary silicon particles and partially spheroidized secondary silicon particles. The secondary silicon particles are about 5 microns diameter, and the primary particles are 15 to 50 microns diameter, but their non-uniform distribution creates critical flaws that are over a millimeter, and that limits the fraction strength of such a commercial alloy. There has been a lot of study on how to modify this primary silicon distribution and size, and here we show the effect of the melt holding temperature and the cooling rate, average solidification rate on that distribution. The slowly cooled material left top corner at 735 degrees and 1.3 degrees a second contains large primary silicons and large plates of secondary plates, and those plates are 250 to 500 microns in diameter and have a thickness of about 5 to 10 microns. And both of those primary and silicons and the secondary silicons, they can form an interconnected network, and that helps the crack propagation through the material. Now, you can see that the commercial engine block that we are talking about, its microstructure lies at the reasonably high melt temperature and the die casting cooling rate of about 35 degrees, or average solidification rate of about 35 degrees a second. And it has been already optimized for that application by the manufacturer. So both the high melt temperature and high solidification rate refine the structure and improve the mechanical properties. There's a question how to improve it more, and there has been a lot of work done with it. All the way back in 1968, Hallowell has published work from a directional solidification of aluminum silicon eutectic alloys solidified in a Bridgman crystal pulling furnace. In this case, you can see a nice eutectic microstructure of needles sectioned perpendicular to the growth direction, and you can see that you can get a very nice even distribution, uniform distribution of such needles. But they're at this cooling rate and growth rate, they are still quite coarse. When he quenched this material in the portion, in a quenched portion of the material, he got this microstructure. And this is still a eutectic composition, but at very fast cooling rate, there are primary aluminum dendrites, and the silicon is then as nanoscale whiskers in the microstructure. And our objective in our work is to reproduce those silicon whiskers in the entire casting. Now, it is very difficult to control while water quenching, so the people add modifiers to change, to control the silicon morphology. The modifiers usually are either alkalis like sodium or potassium, or alkaline earth where the strontium is most used. Those are surface active elements that modify the interfacial surface energy of melt and the silicon, and also interfere with the growth mechanisms for the silicon structures. Now, in this particular case, the modified structure is in the form of a silicon, very fibrous silicon dendrite with submicron fiber diameter. And when on quenching, it was shown that the outer part of it contains coarser Si3 particles and aluminum dendrites on the outer edge. Hallowell, who did the work, attributed those coarser particles forming later and the aluminum dendrites to over-modification, i.e. too much sodium added to the structure. This work has been done by Jenkinson and Hogan in 1974. They were also modifying the aluminum silicon eutectic melt, this time with 500 ppm of strontium. And you can see the section parallel to the growth direction and perpendicular to the growth direction. Again, you get this fibrous dendritic growth of silicon, which is black, but with the fiber diameter of about 250 microns. This is pretty well what we would see as an ideal microstructure to start with for making a silicon dispersed nanocomposite. Now, that type of structure in aluminum in a binary alloy results in the very hard silicon particles in pretty pure ductile aluminum matrix. This aluminum matrix can be further strengthened by artificial aging if you add elements to the alloy that can form spinodal precipitates. In this particular case, you see the work of Ines Hausler, just very recently published, where she worked on artificial aging of aluminum, 4% copper, 1% lithium alloys. And you can see that the microstructure that is produced on peak aging consists of disc-like precipitates. Is shown in the first picture as on edge. And in this particular alloy, there are two types of precipitates, theta prime aluminum copper, and T1, which is aluminum copper lithium. In the higher resolution TEM picture, the second one, you can see both of them at the same time, and you can see that the theta prime is about 2 nanometers thick, and that the interface of the theta prime and the aluminum matrix is quite coherent. So at peak aging, looking at the bottom here, the number of density of theta prime precipitates is about 500 per cubic micron. The diameter of them extends up to about 100 microns. And at peak aging, the volume fraction of theta prime is only about 2.5 volume %. However, because there is because the interface between theta prime and the aluminum is coherent, and there is a certain mismatch in the lattice spacing, there is a very large coherency strain, and this coherency strain improves both hardness and strength. In the top right graph, we can see Brenner hardness increasing from the starting value of about 80 to about 160 at the peak hardness. And that also represents the potential increase in the strength if there is no other critical flaws in the material. Now, for most of the rest of the talk, I'm going to be talking about the work done on the development of our microcomposites by the group at the University of Windsor, led by Professor Sokołowski, who developed a universal metallurgical simulation analysis platform shown in the picture, which allows to melt the sample using induction coil, and then control the cooling at any rate, and log the cooling during solidification and heat treatment. So the physical simulation can do melting, melt treatment, solidification, quenching, and heat treatment. And the analysis has, there's a comprehensive thermal analysis that is done on that. This particular apparatus can heat the metal to 1500 degrees. It can use samples of up to 200 milliliters, and can cool those samples at the rate of up to 30 degrees a second. Now, they've done work on the aluminum silicon copper alloy, and this is what typical slowly cooled microstructure looks like. First, you get the massive silicon particles. Those massive particles nucleate aluminum on them. So the second phase that shows up is aluminum 1 dendrite nucleating on S1 particles, Si1 particles. Then one actually gets an intermetallic, iron intermetallic to form, which is not visible at this magnification. And then you form a secondary or eutectic aluminum plates, which then get covered with secondary dendrites. And then only in the end, you form intermetallic that form in between the aluminum dendrite arms, and in this picture are shown in gold. So understanding of this solidification sequence is a key to developing strategies for microstructure and property optimization. Come on. So here is the thermal data that corresponds to this microstructure, and the graph A shows the cooling curve, and you can see that you can on the cooling curve you can correlate it with the formation of the particular phases in that cooling sequence that I just talked about. Cooling curve is difficult to read. If you differentiate it and look at the cooling rate and draw in the baseline, you can see the thermal peak associated with phase formation much more clearly. And a finer analysis shown in figures C and D allows you to deconvolute the convoluted cooling curve into the individual thermal events. And then picture D shows you how those are then related to the latent heat release from each one of those phases. So again, this comprehensive quantitative understanding is the key to the work to develop something that with the microstructure that you want. To get the samples that I'm going to show you, we needed to also control the pressure. And in this case, the UMSA platform was mounted in the mechanical testing frame and with the melting furnace right in the under the plunger, and there is a high pressure die underneath that, and the metal is melted in the furnace and pushed by the plunger into the hot pressing die, not hot pressing die, but a high pressure die. So in this particular phase, this apparatus can get up to 850 degrees centigrade. Sample is about 10 cubic centimeters, and a pressure of up to 150 megapascals can be applied. And if you're injecting into a cold die, the maximum instantaneous cooling rate can be up to 300 degrees a second. So what was done is a strontium modified aluminum 20% silicon 3% copper alloy was cast in that equipment, and this is the resulting microstructure. The interesting thing is that there is no primary silicon massive crystal, and there is no large aluminum dendrites. The microstructure is dominated by strontium modified silicon 2, secondary silicon, in an aluminum matrix. Those silicon 2 whiskers form in colonies, which we call C-starred colonies, which we'll see in a second why. And at the boundaries in between those colonies, we find a little bit larger Si3 crystals and the Al3 dendrites, very reminiscent to what Hellawell was showing for sodium modified material. And the intermetallics then form again in between the aluminum dendrite arms at the cell boundaries. So again, we are hoping that those Si3 materials are due to the over-modification, as the literature suggests. Here is a picture made by backscatter electron on the scanning electron microscope. This is a very low magnification, and you can see that there are spherical colonies, and which kind of in section look like sea stars. So I call them sea star colonies. And the white material in the picture is bright because it contains copper and reflects the electrons, backscatter the electrons well. So you can see that the copper intermetallics form continuous bridges through the material at the colony boundaries. However, the interior structure of the sea star colonies, the Al2 and Si2, account for more than 90% of the material. And even at this low magnification, one does not see either primary aluminum or primary silicon. One would think that the interconducting continuous brittle network would be a bad news, because in this form, S-cast, it limits the strength of the S-cast composite. Now we deep etched the material to reveal a little bit more of the structure. And again, you can see that the intermetallics are now standing proud of the surface and really show up the microstructure. On the left-hand side, you have the outer edge of the sample, and you have a columnar growth going into the sample for about half a millimeter, and for the rest of the sample, you have spherical colonies of those spherical sea star colonies are the main structures. This is at higher magnifications, showing one of those sea star colonies, and you can see here that the inside of the dendrite arm, and now you can see whiskers that are there. The interesting part of it is that they're edged down, and that implies that the whiskers are not an interconnected dendrites, but individual whiskers which are etched out and removed with the acid etchant. So this is a higher picture of the nanoscale whiskers inside of the arm and the copper intermetallics at the cell boundaries. And this is a picture of the whiskers and the micron marker is at the bottom. And you can see that they're about 220 nanometers average diameter and quite long. And also very uniformly distributed in this inside of that C-star colony structure. If you section and polish the section through this C-star colony arm, you can see that there's not only silicon whiskers there, but there's also some very small fragments of intermetallics that are also less than 500 nanometers in size. And the key point here is that this is the structure that dominates the volume of the entire material and accounts for about 90% of the volume. And the rest is the is the colony boundaries. So we have a structure which is very promising, but we have to improve its ductility by getting rid of the continuous network of brittle intermetallics. How do we do it? We give it a short, about 10 minutes, temperature hold near the maximum temperature of the stability of aluminum plus silicon in the phase diagram. This is below the silicon solvus surface, but it is above the aluminum silicon copper intermetallic solvus surface. So what happens is that silicon whiskers and the smaller Si3 platelets break up and spherodize into aqueous, ultrafine, still mostly submicron silicon particles. And the aluminum intermetallics mostly dissolve in the aluminum to form aluminum solid solution matrix. So here is a comparison between S-cast and solution treated structure. And you can see that the aluminum now is a solid solution matrix that now contains most of the copper, and the intermetallics are mostly gone, dissolved in aluminum silicon. The silicon 2 has coarsened, but it is still mostly about 500 nanometers. The little larger Si3 platelets at the grain boundaries sometimes spherodize, sometimes stayed at platelets, but they're still less than 10 microns, and they're isolated from each other rather than forming networks. So in a deep-etched scanning electron picture, you can now see that where you used to have the colony boundaries, you can still find some silicon-3 platelets, but they're typically less than 10 microns. And the Si2 in the colony arms are still sub-micron. And here is a higher picture of those sub-micron spheroidized silicon particles in the colony arm. So if we now compare the structure of the sample that was produced on the high pressure dicamsing UMSA to what is commercial in the Yamaha engine block, you can see that the largest particle at the lower magnifications in the UMSA sample are about 10 microns, whereas in the Yamaha engine blocks, those are agglomerates over 100 microns, which concentrate into even larger flows. Looking at the secondary silicon, long thermal treatment of the engine block partially spheroidized those, but they're 5 microns and around 5 microns, whereas short treatment on of our nanocomposites managed to spheroidize the particles without getting them too much above 500 nanometers. Now, we already talked about other people artificially aging to strengthen the material. And to do that, we have now, after solution treatment, a supersaturated aluminum solution with about 4% copper in it, because we took out the silicon out of aluminum 3% copper alloy. So in this particular case, artificially aging means a temperature hold at about 150 to 200 degrees centigrade, and one needs less than 10 hours to reach peak strength and peak hardness. So in this process, the supersaturated matrix, aluminum matrix, undergoes age hardening by spinodal decomposition. So here are the pictures of the comparison of the engine block and UMSA sample, solidified sample, after artificial aging. You can see the silicon in purple, and the copper is in blue, and theta prime nanoscale precipitates are actually barely visible in the aluminum matrix, but they are there, and they contribute to the hardness of the matrix after artificial aging. In the engine block, which had a much longer aging treatment and solution treatment, the theta precipitates are significantly bigger, and there are also still undissolved large particles, intermetallic particles that contain copper, magnesium, and silicon, and aluminum, copper, and iron. And Si2 particles, again in purple, are now over 5 microns. So comparing those to the microstructure, one expects significantly improved H100 properties for the high pressure die-cast material. So let's take a look at the hardness for those, comparing those materials. S-cast A, the solution treated with very short artificial aging, B, solution treated and a little bit longer artificial aging, C, and the high pressure die-cast commercial block, which undergoes an 8-hour solution treatment and artificial aging. So you can see that with our case C, we get 23% improvement in the Vickers hardness of the material, of the micro hardness of the material, and over the HPDC block. And interestingly, you can see that the improvement from the S-cast material A to C is 43%. If you look at the macro hardness, this is a Rockwell B hardness. You can see that the Rockwell B hardness for the artificially aged sample C is 20% more than the block material for thicker portion of the wall, and you can also see that even for the commercial material, the hardness depends on the cooling rate, because the thinner portions of the wall are harder than the thicker portions of the wall. So you have an improved hardness in 7 millimeters and 15, but the new material is 20% harder than the commercial material. Now, tensile test samples are still to be produced, but while engineers often use an approximate empirical linear correlation between a macro hardness measurement and a potential tensile test of metal alloys. And so if you look at our Rockwell B measurements of 72 and 86, they would compare to a potential tensile strength, potential because it requires that there are no other reasons for degrading the strength, of between 435 and 570, up to 570 megapascals. Now, 570 megapascals is the domain of the automotive, aerospace, aircraft alloys such as 7000 series and 2000 series rod alloys. If one looks at the wear of the samples, you can see here the groove depth of in reciprocated wear test, and if you look at the wear, we're looking at three cases: a strontium modified version of the alloys, but cast without pressure application. The unmodified alloy cast in the high pressure die casting simulator, and then the modified nanostructured material as cast in the under pressure in UMSA. So you can see that S-cast material has a 51% less wear than the non-pressurized melt. So making the material under high pressure die casting conditions is very much desired. It is now this is for S-cast material. After artificial aging, we would expect that the wear performance will be still better than what we're showing here. So that's where the work stands on the laboratory scale, and Phinix is proposing stage 4 proposal for lift, with the objective of improvement of specific mechanical material properties of aluminum-based alloys, including strength, hardness, and wear resistance, while retaining adequate toughness and ductility for property-critical application and transportation by first processing the industrial-grade aluminum, silicon, and something else hypereutectic alloys to generate novel S-cast nanoviscous structures free of detrimental primary and secondary silicon. To a short solution treatment generating nano and ultrafine nodular silicon particles uniformly distributed in aluminum solution matrix. And 3, optimum addition of minor alloying elements that we label X, which are maybe copper, magnesium, or zinc, that modify matrix properties through spinodal decomposition of the aluminum solid solution, supersaturated solid solution, and solid state precipitation of nanoscale coherent spinodal precipitates during artificial aging. This is our target. So this is our material that has been already done on the lab scale. It is 26 volume% of pretty uniformly distributed ultrafine silicon, and there is a little bit of residual intermetallic, all isolated. There is also 2.5 volume of nano-size spinozal precipitates in the aluminum matrix, strengthening the whole thing. What are the potential applications of such a thing? Well, it depends on which advantage you can want to take advantage of. HP die casting can make thin-walled, complex net shape, leading to parts consolidation, and an aerospace that can be useful in housings, seat frames, instrument panels, and the same thing for automotive. One can take advantage of high hardness and low wear, and that's useful in latches and hinges in aerospace, which can have very complex shapes. And in automotive, where engines are a little bit less temperature critical, one already use this chemistry for pistons and cylinder liners. One can take the advantage of low density for the high specific strength and stiffness, and use this type of materials as stiffening ribs or landing gear components. And in automotive, the inner structure of the automobile and suspension components can be some targets. This process flow sheet for this type of a process is pretty well totally standard. Melting, alloying, melt treatment, modifying addition, casting, and heat treatment. There's nothing magic or difficult about any one of the process steps. That makes it a low cost process, low risk process, and allows for us to have a target of significant improvement in specific mechanical properties without significant increase in component costs. Further, the starting materials and aluminum and the alloying elements are all abundant and readily available and can be actually sourced in many cases from secondary recycled sources. The process is fast. The solidification takes less than 10 seconds. Solution treatment, less than 10 minutes. And artificial aging, less than 10 hours. So that gives us a potential for very low cost process, for the material that can be recycled back into A390 alloy, and that can be batched from recycled materials. So we have the state round for proposal submitted to LIST to work on that this type of materials, and Phinix is looking for partners of the gold or silver to move forward with the project under LIST umbrella. Thank you very much. I presented, I'm Adam Guessing, but the contact for anybody that is interested is shown here as Dr. Subodh Das, who runs Phinix. Thank you very much. Any questions?
Thank you very much. Thank you very much, Adam. Appreciate your presentation. I did not see any questions come in. Well, I did have one question. I know we're running up at the top of the hour, but someone wanted to know how did you avoid the solidification of the coarse primaries silicon particles? They may have missed that question, but how did you go ahead and avoid that?
There are two factors. One is if you do it fast enough, it doesn't have enough time to nucleate and form. So the high solidification rate is one key aspect. The other aspect is right amount and the right type of a modifier. which in our case was strontium, and the modifier again interferes with the nucleation of silicon and also interferes with the growth rate of silicon, especially in the modes that are that lead to massive particle growth and plate type growth. So they promote both dendritic, fibrous, and whisker formation.
And what was the thickness of the casting?
The thickness, the sample was 20 millimeter diameter, 30 centimeter long.
And
so this is a laboratory size sample made in the casting simulator. And what we are aiming at now, and we already have dies designed to cast dog bone type tensile test samples, and we are looking forward to trying to match the process conditions that we achieved in the casting simulator in the real high pressure die casting dies under industrial conditions.
Excellent, thank you. I know we are at the top of the hour, a little bit past, so I wanted to thank again Phinix for presenting this month. Next month, stay tuned to lift.technology/liftoff to see the schedule of upcoming speakers, including next month, which I believe is the 19th of October. One more thing I wanted to mention to folks who are in the Detroit area, we are opening with IACME, our sister institute here in Detroit. We are unveiling our high bay area that we've invested in over the course of the last year. There's been construction going on just about every day for the course of last year, with some large scale manufacturing equipment both on the metal side and the composite side. So we're hosting an open house on Manufacturing Day, which is Friday, October 6th. You can RSVP to that and find more information right on our website at lift.technology, and we look forward to seeing you. So that concludes this month's Liftoff webinar. Certainly appreciate your participation, and we look forward to seeing you next month. Thank you so much.